What if I told you that right now, as you listen to these words, light from a world with two suns is washing over your skin? That the photons entering your eyes left distant planets where iron rains from broiling skies, where crimson oceans might lap against alien shores, where something, perhaps, is gazing up at its own night sky and wondering the exact same thing you are. Am I alone? We've found them, thousands of worlds beyond our solar system, planets where a year lasts 4 Earth days, planets made of diamond and graphite, worlds so hot that rocks vaporize into clouds, and worlds so cold that methane lakes freeze solid under skies of perpetual twilight, gas giants hugging their stars at impossible distances, rocky worlds 3 times the size of Earth, planets orbiting dead stars, planets with no stars at all, wandering the galaxy like cosmic orphans. And nestled among them, perhaps more common than we ever dared hope, are worlds in that perfect range of distance from their stars where water could pool, where atmospheres could stabilize, where the ancient chemistry of life might have had billions of years to unfold. But here's what makes this extraordinary. 30 years ago, we had no proof any of this existed. For all of human history, the only planets we knew were the 8 circling our sun. We wondered, yes. We dreamed. But we couldn't be certain. Then, in a single year, everything changed. A discovery was made that would rewrite our place in the cosmos and spark a scientific revolution that continues to this moment. Tonight, we're going to explore that revolution, from its startling beginning to the discoveries being made right now that might finally answer humanity's oldest question. For most of human history, we could only imagine such worlds. The planets of our own solar system, 8 worlds circling our sun, were the only ones we knew. We wondered, yes, we dreamed, but we had no proof. Then, not quite 3 decades ago, everything changed. We found them. Not 1, not 10, but thousands of planets orbiting other stars, each one rewriting what we thought we knew about how planets form, where they can exist, and what conditions might harbor life. These are the exoplanets, worlds beyond our solar system, and their discovery has transformed our understanding of the universe and our place within it. Hello there, and welcome to Sleepable Science. I'm so glad you found your way here. Tonight, we're embarking on a journey far beyond the familiar bounds of our solar neighborhood. We'll drift through distant star systems, pause at worlds that defy imagination, and explore the tools and methods that have revealed this hidden cosmic population. Whether you've had a long day or simply find comfort in the vastness of space, this is your time to rest, to wonder, and to let your thoughts float gently among the stars. You don't need to do anything but listen. Let your breathing slow. Let the weight of the day fall away like dust settling on our distant planet's surface. Because tonight, we're not just talking about dots of light or abstract numbers in a database. We're talking about real places, real worlds, each with its own story written in starlight and shadow. Some may be cold and silent, others might roar with storms that dwarf anything Earth has ever known. And a few, just a precious few, might be just right. Before we begin our exploration, if you find these gentle journeys through science help you unwind or spark your curiosity, as you drift toward sleep, consider liking and subscribing to Sleepable Science. It helps others discover this quiet corner of wonder, one sleepy soul at a time. Now, settle in, close your eyes if you wish, and let's begin our voyage to the planets beyond. The dawn of discovery. For centuries, astronomers dreamed of finding planets around other stars. It seemed like it should be possible. After all, if our sun has planets, why wouldn't other stars? The logic was sound, but the challenge was immense. Planets don't produce their own light. They're tiny compared to their parent stars, and they're separated from us by distances so vast that even light takes years or decades to reach Earth. Finding an exoplanet is like trying to spot a firefly hovering next to a searchlight from hundreds of miles away. The glare overwhelms, the distance obscures, and yet astronomers persisted. The first confirmed exoplanet discoveries came in 1992, but they weren't quite what anyone expected. They orbited a pulsar, the rapidly spinning remnant of a dead star called PSR B1257+12. These weren't the gentle, nurturing environments anyone hoped to find. Pulsars are extreme objects, neutron stars no larger than cities, but containing more mass than our Sun, spinning hundreds of times per second and blasting radiation into space with each rotation. Finding planets there was extraordinary, yes, but also somewhat disheartening. These worlds orbited in a hellscape of radiation. They told us planets could exist in the strangest places, but they didn't quite capture the public imagination. The real breakthrough came 3 years later, on October 6, 1995, when two Swiss astronomers, Michel Mayor and Didier Queloz, announced a discovery that would change everything. They had found a planet orbiting a Sun-like star called 51 Pegasi, located about 50 light-years away in the constellation Pegasus. The planet, designated 51 Pegasi b and later given the formal name Dimidium, was nothing like astronomers expected. It was a gas giant, about half the mass of Jupiter, but it orbited its star in just 4 Earth days. 4 days. For comparison, Mercury, the innermost planet in our solar system, takes 88 days to orbit the Sun. This planet was hugging its star at a distance of just 7.8 million kilometers, far closer than Mercury's 58 million kilometers from the Sun. Mayor and Queloz had detected the planet using a technique called the radial velocity method, sometimes known as the Doppler wobble method. As a planet orbits its star, it doesn't actually orbit a fixed point. Instead, both the planet and the star orbit their common center of mass, a point somewhere between them but much closer to the star because the star is so much more massive. This causes the star to wobble ever so slightly back and forth. As the star moves toward Earth, its light is compressed to shorter, bluer wavelengths. As it moves away, the light stretches to longer, redder wavelengths. This is the Doppler effect, the same phenomenon that changes the pitch of a passing siren. By carefully measuring these tiny shifts in the star's spectrum, astronomers can detect the presence of an unseen planet and even calculate its mass and orbital period. The announcement sent shockwaves through the astronomical community. A gas giant orbiting so close to its star contradicted everything planetary formation theory predicted. Gas giants were supposed to form far from their stars, beyond what's called the snow line, where temperatures are cold enough for water and other volatiles to freeze into ice. These ices provide the solid material needed to build large planetary cores that can then attract enormous atmospheres of hydrogen and helium. Close to a star, it's too hot for ices to form. So how could a Jupiter-sized planet end up practically skimming its star's surface? The discovery was so unexpected that many astronomers were skeptical at first. Could it be a mistake? Could the signal come from something else? Perhaps stellar activity or pulsations? But within a week, another team of astronomers at Lick Observatory in California confirmed the finding. 51 Pegasi b was real, and it was the first of a new class of planets that came to be known as hot Jupiters, gas giants orbiting perilously close to their stars, with surface temperatures soaring into the thousands of degrees Fahrenheit or Celsius. For this discovery, Michel Mayor and Didier Queloz were awarded the 2019 Nobel Prize in Physics, more than 2 decades after their groundbreaking announcement. The prize recognized not just a single discovery, but the opening of an entirely new field of astronomy. Because once astronomers knew that planets could exist in such unexpected configurations, they began finding them everywhere. The techniques improved, the instruments became more sensitive, and the floodgates opened. Within a few years, dozens of exoplanets had been discovered. Within a decade, hundreds. Today, as of 2025, we've confirmed more than 6,000 exoplanets, with thousands more candidates awaiting confirmation. What 51 Pegasi b taught us was profound. Planets don't always stay where they form. Based on what we understand about planetary formation, the hot Jupiters almost certainly formed far from their stars, in the cold outer regions where gas giants are supposed to be. But then, the evidence suggests, through gravitational interactions with other planets or with the disk of gas and dust from which they formed, they migrated inward, spiraling closer and closer to their stars over millions of years. Some, we can infer, were captured in stable orbits. Others may have fallen into their stars entirely, leaving no trace. The planetary systems we observe today are the survivors, those that found stable configurations after what may have been eons of orbital chaos. This discovery fundamentally changed how we think about planetary systems. Our own solar system, with small rocky planets close to the Sun and gas giants farther out, is just one possible arrangement. Nature experiments with many others, and each discovery since 51 Pegasi b has revealed new variations, new surprises, new questions. The universe, it turns out, is far more creative than we ever imagined. Methods of detection. Finding exoplanets requires ingenuity. These worlds are small, dark, and overwhelmingly outshone by their parent stars. To detect them, astronomers have developed several clever techniques, each with its own strengths and limitations. Understanding these methods helps us appreciate not just what we've found, but how we found it, and what we still might be missing. The radial velocity method, which revealed 51 Pegasi b, remains one of the most powerful techniques. It works best for detecting massive planets in close orbits because these create the largest wobble in their stars. The speed at which a star moves toward and away from us can be measured with extraordinary precision, down to changes of just a few meters per second, about the speed of a person walking. This sensitivity allows astronomers to detect even relatively small planets if they orbit close to their stars. However, the method has limitations. It provides a minimum mass for the planet, not the exact mass, because the inclination of the orbit relative to our line of sight is often unknown. A planet whose orbit we view edge-on creates a different signal than one we view from above. Additionally, stellar activity like spots and flares can mimic the signals of planets, so careful analysis is needed to distinguish real planets from false alarms. The transit method has become the workhorse of exoplanet discovery, particularly with space-based missions like NASA's Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, known as TESS. This technique is beautifully simple in concept. If a planet's orbit happens to be aligned just right, the planet will periodically pass in front of its star as seen from Earth, blocking a tiny fraction of the star's light. By continuously monitoring a star's brightness, astronomers can detect these periodic dips and infer the presence of a planet. The amount of light blocked tells us about the planet's size. A larger planet blocks more light, creating a deeper transit. The time between transits tells us the orbital period, and the duration of the transit, combined with properties of the star, can tell us how far the planet is from its star. For a planet, the size of Earth transiting a sun-like star, the brightness drops by about 0.008%, less than 1 part in 10,000. For larger planets or smaller stars, the signal is stronger. Hot Jupiters, being both large and close to their stars, transit frequently and create deep dips, making them relatively easy to find despite their rarity. This is one reason why hot Jupiters dominated early exoplanet catalogues, not because they're common, but because they're easy to detect. The Kepler mission, launched in 2009, revolutionized the field by staring at a single patch of sky containing about 150,000 stars for nearly 4 years. By watching continuously, Kepler could detect multiple transits of the same planet, confirming its periodic nature and ruling out one-time events like asteroids or measurement errors. Kepler discovered more than 2,600 confirmed exoplanets and identified thousands more candidates still awaiting confirmation. The mission revealed that planets are incredibly common. Statistical analysis of Kepler data suggests there are more planets than stars in our galaxy, potentially hundreds of billions of worlds. One of the transit method's great advantages is that it can be combined with other techniques. During a transit, light from the star passes through the planet's atmosphere, and different molecules in that atmosphere absorb light at specific wavelengths. By carefully analyzing the spectrum of light during the transit and comparing it to the spectrum when the planet is not transiting, astronomers can detect the chemical fingerprints of gases in the atmosphere. This technique, called transmission spectroscopy, has revealed water vapor, carbon dioxide, methane, and other molecules in exoplanet atmospheres. It's one of our most powerful tools for characterizing these distant worlds, for turning them from mere dots of light into actual places with weather, chemistry, and perhaps even the potential for life. Direct imaging, the most intuitive method, is also the most challenging. This technique involves taking actual pictures of exoplanets by blocking out the overwhelming light of their parent stars. Special instruments called coronagraphs or star shades are used to mask the star's glare, allowing the faint reflected or emitted light from the planet to be detected. Direct imaging works best for young, massive planets orbiting far from their stars. Young planets are still hot from their formation, radiating infrared light that makes them easier to see. Large planets reflect more light and have stronger infrared emissions, and the farther a planet is from its star, the easier it is to separate the two in an image. Direct imaging has successfully photographed several planetary systems, revealing the architecture of these alien worlds. In 2008, astronomers captured images of the HR 8799 system, showing 4 giant planets orbiting a young star about 130 light-years away. These images, updated over subsequent years, show the planets moving, in their orbits, visual proof of their existence and motion. More recently, direct imaging has captured planets still in the process of forming, embedded in the disks of gas and dust surrounding newborn stars. These observations provide crucial insights into how planets assemble from raw material. Gravitational microlensing offers a completely different approach, exploiting Einstein's general theory of relativity. When a star passes in front of a more distant background star as seen from Earth, the foreground star's gravity acts like a lens, bending and magnifying the light from the background star. If the foreground star has a planet, the planet's gravity creates an additional, distinctive spike in the light curve. Microlensing events are rare and brief, lasting only a few days or weeks, but they can detect planets at a wide range of distances from their stars, including cold planets far from their suns that would be nearly impossible to find by other methods. One significant advantage is that microlensing can find planets around faint stars or even free-floating planets drifting through interstellar space without any star at all. Astrometry, the precise measurement of stellar positions, is one of the oldest astronomical techniques, but one of the newest for exoplanet detection. Just as a planet's gravity causes its star to wobble in velocity, it also causes the star to move slightly in position on the sky. These movements are incredibly tiny, but with space-based telescopes capable of extraordinary precision, such as the European Space Agency's Gaia mission, astrometry is beginning to detect planets by tracking these positional shifts over time. Gaia is creating the most precise three-dimensional map of our galaxy ever made, measuring the positions and motions of over 1 billion stars. Among these measurements, hidden signals reveal the presence of unseen planetary companions. Each method has its biases. Radial velocity favors massive planets close to their stars. Transit searches favor large planets with short orbits, especially around small stars where the transit signal is strongest. Direct imaging favors young, massive planets far from their stars. Microlensing can find planets at any distance, but requires rare alignment events. Only by combining multiple methods can we get an unbiased picture of the planetary population. When a planet is detected by more than one method, the combination is powerful. Radial velocity gives the planet's mass, transit gives its size, and from these we can calculate density, telling us whether the planet is rocky like Earth, icy like Neptune, or gaseous like Jupiter. Together, these techniques have painted a picture of extraordinary diversity. The evolution of detection methods mirrors the history of exoplanet science itself. In the early days, astronomers relied heavily on radial velocity because it required only spectroscopy, a well-established technique. Ground-based telescopes equipped with high-precision spectrographs could measure stellar wobbles from observatories around the world. The HARPS instrument on the European Southern Observatory's telescope in Chile became a workhorse of exoplanet discovery, capable of detecting velocity changes as small as 1 meter per second. That's the speed of a person walking slowly. At that level of precision, even Earth-mass planets orbiting in habitable zones around smaller stars become detectable. But radial velocity has limitations beyond just favoring massive, close-in planets. Stellar activity can confound measurements. Stars have spots, flares, and pulsations that can mimic planetary signals. A rotating star with dark spots will show periodic velocity variations as the spots rotate into and out of view, changing the average brightness and thus the apparent velocity through asymmetric heating. Distinguishing these false positives from real planets requires careful analysis, often combining velocity measurements with photometric monitoring to track stellar activity independently. The transit method overcame some of these limitations, but introduced others. Because transits require the planet's orbital plane to be nearly edge-on as seen from Earth, only a small fraction of planets are geometrically favorable. For a planet in an Earth-like orbit around a Sun-like star, the probability of observing a transit is less than 1%. But by observing hundreds of thousands of stars simultaneously, missions like Kepler could discover thousands of planets despite the low probability for any individual system. Kepler's strategy was to stare at a fixed patch of sky, monitoring the same stars continuously. This allowed detection of multiple transits, confirmation of periodicity, and measurement of orbital characteristics with high precision. Transit timing variations, the slight changes in when transits occur, provide additional information. If a planet orbits alone, its transits are perfectly periodic. But if other planets are present, their gravitational interactions cause small variations in orbital periods. These timing variations can reveal the presence of additional planets that don't themselves transit, determine planetary masses through dynamical modeling, and constrain the orbital architecture of the entire system. The TRAPPIST-1 system's masses, for example, were largely determined through transit timing variations, as the 7 tightly packed planets constantly tug on one another. Space-based transit surveys have advantages over ground-based ones. Earth's atmosphere introduces noise through scintillation, the twinkling of stars caused by turbulent air. From space, stars don't twinkle, allowing more precise photometry. Additionally, space telescopes can observe continuously without interruption from daylight, weather, or the rotation of Earth. This continuous coverage is crucial for detecting planets with longer orbital periods, which transit infrequently. A planet orbiting once per year only transits once per year, and missing even one transit can delay confirmation by an entire orbital period. The complementary nature of detection methods means that combining them yields far more information than either alone. When both radial velocity and transit observations exist for the same planet, astronomers can determine both the planet's mass and its radius. From these two measurements, they can calculate the planet's density, a fundamental property that reveals its composition. A density similar to Earth's, about 5.5 grams per cubic centimeter, suggests a rocky world with an iron core. Lower densities indicate substantial water or ice, or thick gaseous envelopes. Very high densities might indicate pure iron composition or unusual internal structures compressed by extreme gravity. Atmospheric characterization through transmission and emission spectroscopy extends the power of transit detections even further. Not only do we learn that a planet exists and determine its basic properties, we can probe its atmosphere, looking for specific molecules, measuring temperature profiles, and even detecting winds and weather systems. For some well-studied exoplanets, we now know more about their atmospheres than we know about the atmospheres of some planets in our own solar system. We can measure atmospheric composition, temperature as a function of altitude, cloud properties, and the presence or absence of hazes. These observations transform distant exoplanets from abstract concepts into actual tangible worlds with measurable properties. The Gallery of Strange Worlds. The exoplanets we've discovered are almost too diverse to categorize neatly. They range from rocky worlds smaller than Earth to bloated gas giants several times more massive than Jupiter. Some are scorched by their stars, while others drift in eternal cold. Let's wander through this cosmic gallery and meet some of the most intriguing inhabitants. Hot Jupiters remain among the most dramatic discoveries. These are gas giants, worlds of hydrogen and helium with no solid surface. But unlike Jupiter's leisurely 12-year orbit around the Sun, hot Jupiters complete their orbits in just days or even hours. 51 Pegasi b, the first discovered, has a year of just 4 days. Others are even closer. WASP 12b orbits its star once every 1.1 Earth days at a distance so small that the star's gravity is literally pulling the planet apart, stretching it into an elongated shape and stripping away its atmosphere. The dayside temperatures on hot Jupiters often exceed 2,000 degrees Fahrenheit, sometimes over 3,000. At these temperatures, metals like titanium and iron can vaporize, forming clouds that rain molten glass or even iron. The intense heat drives ferocious winds that circulate around the planet at supersonic speeds, redistributing heat from the scorched day side to the cooler night side, though even the night side remains blazingly hot by any earthly standard. Super-Earths occupy a size range with no analog in our solar system. These are rocky planets more massive than Earth, but smaller than Neptune, typically between 2 and 10 times Earth's mass. They're incredibly common, possibly the most common type of planet in the galaxy, yet we have no local example to study up close. What are they like? Are they scaled-up versions of Earth with thicker atmospheres and stronger gravity? Or are they mini-Neptunes with deep hydrogen envelopes over rocky cores? The answer likely depends on where and how they formed. Some super-Earths may be ocean worlds, planets entirely covered by water hundreds of kilometers deep, heated from below by internal heat, and blanketed above by thick, steamy atmospheres. Others might be dry, rocky planets with thin atmospheres or none at all, scorched by their stars or stripped by stellar winds. Mini-Neptunes are slightly larger than super-Earths, with thick atmospheres of hydrogen and helium that puff them up but not enough mass to become full gas giants. These worlds likely have rocky or icy cores, surrounded by deep atmospheres that transition gradually from gas to liquid under enormous pressure. Like super-Earths, mini-Neptunes are extremely common but absent from our solar system. The boundary between a super-Earth and a mini-Neptune is fuzzy, a continuum rather than a sharp divide. Interestingly, astronomers have noticed a gap in the size distribution of small planets, a range between about 1.5 and 2 Earth radii, where planets seem less common. This radius valley, also called the Fulton Gap, may represent a critical size threshold. Planets that grow larger than this quickly attract thick hydrogen atmospheres and balloon into mini-Neptunes, while those that remain smaller keep thin atmospheres or lose them entirely, remaining as rocky super-Earths. Rogue planets are perhaps the most mysterious of all, worlds without stars. These planets drift through interstellar space, ejected from their birth systems by gravitational encounters with other planets or with passing stars. They receive no light or heat from a parent star, their surfaces frozen in eternal night. Some may retain internal heat from their formation or from radioactive decay in their cores, perhaps enough to maintain subsurface oceans beneath icy shells, similar to what we suspect exists on Jupiter's moon Europa or Saturn's moon Enceladus. Rogue planets are difficult to find because they emit little light and no star pinpoints their location. Most have been detected through gravitational microlensing or by observing the faint infrared glow from residual heat. Statistical estimates suggest there could be as many or even more rogue planets than stars in the galaxy, billions or trillions of worlds wandering alone through the dark. They are the orphans of planetary formation, cast out into the night. Lava worlds are planets so close to their stars that their surfaces are molten, oceans of liquid rock covering entire hemispheres. Planets like 55 Cancri, a super-Earth orbiting a Sun-like star about 41 light-years away, likely have surfaces of molten silicon and metals heated to over 2,000 degrees Celsius. Observations from the James Webb Space Telescope suggest 55 Cancri. It may have an atmosphere, possibly composed of gases bubbling up from its magma ocean, a thick blanket of carbon dioxide or carbon monoxide constantly being replenished as the surface boils. These worlds challenge our understanding of what conditions can exist on planets and whether any kind of chemistry, any kind of complexity can survive in such extreme heat. Ocean worlds, or Hycean planets, represent a category that has recently gained attention. The hypothesis suggests these could be large planets with liquid water oceans beneath hydrogen-rich atmospheres. Unlike Earth's thin atmosphere, which exerts just one atmosphere of pressure at sea level, theoretical models indicate Hycean planets might have atmospheres many times thicker, pressing down on oceans potentially hundreds of kilometers deep. Despite what would be alien conditions by Earth standards, liquid water combined with the energy from the star and a stable environment could, researchers theorize, support life. The chemistry would be fundamentally different from Earth's, the pressure's intense, but the basic ingredients, water, energy, and time, would be present. K2-18b, a planet 8.6 times more massive than Earth orbiting a red dwarf star about 120 light-years away, is a leading candidate for this class. Observations from the James Webb Space Telescope have detected carbon dioxide and methane in its atmosphere, findings that are consistent with predictions for a water-rich world and have tentatively detected dimethyl sulfide, a gas on Earth produced almost exclusively by marine phytoplankton. If confirmed through additional observations, this could represent the first detection of a potential biosignature on an exoplanet, though scientists emphasize caution is essential. Alternative explanations involving exotic non-biological chemistry would need to be thoroughly ruled out before drawing conclusions about life. Diamond planets are a fascinating theoretical possibility born from the chemistry of planet formation. In stellar systems rich in carbon relative to oxygen, theoretical models suggest planets might form with very different compositions from Earth. Instead of silicate rocks, these worlds could theoretically have surfaces and interiors rich in carbon compounds like graphite and diamond. One such planet, 55 Cancri E, orbits so close to its star that much of it is likely molten, but computer models indicate a significant fraction of its mass could be carbon. Whether that carbon exists in the form of diamond or some other high-pressure phase remains a subject of scientific debate, but the concept captures the imagination. If such planets exist as theory predicts, they might have cores not of iron and nickel, but of compressed carbon, where mountains could conceivably glitter like jewels if anyone were there to observe them. Puffy planets, ultra-low density worlds, are gas giants so inflated by their star's heat that they have the mass of Saturn but the radius of Jupiter or larger. Their average densities are less than that of water, some comparable to styrofoam. These planets are bloated balloons, their atmospheres heated to such high temperatures that they expand dramatically. The exact mechanisms aren't fully understood, but intense stellar radiation, possibly combined with energy from gravitational tides, keeps these planets puffed up. Studying them helps astronomers understand atmospheric dynamics under extreme conditions. Then there are circumbinary planets, worlds that orbit two stars at once. These are the real-life versions of Star Wars Tatooine. When two stars orbit each other, their combined gravity can capture planets in stable orbits around both stars. Several such systems have been discovered, including Kepler-16b, a Saturn-sized planet orbiting a pair of stars about 200 light-years away. Standing on such a planet, you would see two suns rise and set, each following its own path across the sky. The light levels would change dramatically depending on whether both stars were in the sky, one was, or neither, creating a complex pattern of day and night unlike anything in our solar system. Each new discovery adds to this gallery, and the variety seems endless. There are planets with glass raining sideways in high-speed winds. Planets where one side eternally faces the star, baked in perpetual day, while the other freezes in endless night, with a narrow twilight zone between them where temperatures might be moderate. Planets orbiting dead stars, cooling slowly over billions of years. Planets so old they formed when the universe was young, before most of the heavy elements we take for granted had been made by stars. And undoubtedly, planets we haven't yet imagined, waiting to be discovered in future surveys. Water worlds or ocean planets deserve special attention. Some super-Earths may be entirely covered by liquid water oceans, hundreds or even thousands of kilometers deep. Unlike Earth, where oceans are just a few kilometers deep on average, these worlds would have no continents, no land masses, just a global ocean extending down until the immense pressure turns water into exotic high-pressure ices even at temperatures far above freezing. At the bottom of such oceans, strange forms of ice, Ice 7 or Ice X, compressed by the weight of kilometers of water above, would form a solid layer separating the liquid ocean from a rocky mantle below. The surface would be an endless expanse of water, possibly with clouds and rain, perhaps even storms rivaling anything on Earth. The chemistry in such deep oceans, under high pressure and with minimal contact with rock, would be fundamentally different from Earth's oceans. Eyeball planets are a theoretical class that could potentially exist around red dwarf stars. Because planets in the habitable zones of these cool stars would likely be tidally locked, one hemisphere would always face the star while the other faces away into eternal night. Climate models suggest that if such a planet had water, it might freeze everywhere except for a circular region on the day side, directly beneath the star. From above, theoretical renderings indicate the planet would resemble an eyeball, with a pupil of liquid water surrounded by an iris and sclera of ice. The ice would be kilometers thick on the night side, gradually thinning toward the twilight zone, where it meets the liquid water region. The boundary between ice and water, based on these simulations, would be a narrow band circling the planet, a ring of coastline where temperatures hover near freezing. Atmospheric circulation models predict winds would blow from the warm day side to the cold night side, creating weather patterns unlike anything on Earth. Desert worlds, planets with little or no surface water, are also possible. Venus in our solar system is such a world, though its surface is hidden beneath thick clouds. Exoplanets closer to their stars than the habitable zone might lose all their water through a runaway greenhouse effect, where rising temperatures cause oceans to evaporate, water vapor traps even more heat, and eventually the water is broken apart by ultraviolet light, with hydrogen escaping to space. What remains is a hot, dry world with a thick carbon dioxide atmosphere and perhaps residual traces of water vapor, but no liquid water anywhere. Some planets might never have had much water to begin with, forming from dry materials in regions of their protoplanetary disks where volatiles were scarce. Carbon planets, worlds where carbon chemistry dominates instead of silicon chemistry, represent a radically different kind of rocky planet. Earth and the other terrestrial planets in our solar system are made primarily of silicate minerals, compounds of silicon and oxygen. But in stellar systems with high carbon-to-oxygen ratios, planets could form with a very different chemistry. Instead of silicate rocks, their interiors might be composed of silicon carbide, titanium carbide, and other refractory carbon compounds. Under the high pressures in planetary interiors, pure carbon could form graphite and diamond layers. Some models suggest carbon planets could have crusts of graphite or diamond, mantles of silicon carbide, and cores of iron carbide rather than pure iron. Whether such planets actually exist is still uncertain. Observations of exoplanet atmospheres and interior models will help determine if this exotic class of worlds is real or merely theoretical. Planets with extreme eccentricity, orbits that are highly elliptical rather than nearly circular, experience dramatic seasonal variations unlike anything in our solar system. As they swing close to their stars at periastron, the closest point in their orbits, temperatures soar. Atmospheres may be heated intensely, driving strong convection and storms. Then, as they move to apastron, the farthest point, they cool dramatically, possibly freezing out atmospheric gases into surface ices. These extreme swings would stress any ecosystems unfortunate enough to exist on such worlds, though life on Earth has proven surprisingly adaptable to harsh environments. Sub-Earths, planets smaller than Earth, are less common in detection statistics, largely because they're harder to find, but they undoubtedly exist in large numbers. Some are probably similar to Mercury, small rocky worlds with little or no atmosphere, heavily cratered and tidally locked. Others might resemble Mars, with thin atmospheres, ancient dry riverbeds, and polar ice caps. The smallest planetary objects blur the line between planets and moons. Pluto, in our solar system, would be considered a large sub-Earth if it orbited a distant star. In other systems, similar small bodies might exist not just in cold outer regions, but also closer to stars, scorched, and airless. The habitable zone. Among all these exotic worlds, a special subset captures particular attention. Planets in the habitable zone, often called the Goldilocks zone, after the fairy tale character who preferred things not too hot, not too cold, but just right. The habitable zone is the region around a star where a planet with the right atmospheric conditions could maintain liquid water on its surface. Liquid water is essential for life as we know it. It's the medium in which biochemistry happens on Earth, the solvent for proteins and nucleic acids, the substance that moderates temperatures and enables the complex chemistry of living cells. The habitable zone isn't a fixed distance, but varies with the star's temperature and brightness. Around a hot, luminous star like Sirius, the habitable zone would be far out, perhaps several astronomical units, the distance from Earth to the Sun. Around a cool, dim red dwarf, the habitable zone might be just a few million kilometers from the star, closer than Mercury is to our Sun. This is because cooler stars emit less energy, so a planet must orbit closer to receive enough warmth. Around Sun-like stars, the habitable zone extends roughly from 0.95 to 1.4 astronomical units, with Earth, of course, sitting comfortably near the middle at 1 astronomical unit. But the habitable zone is more concept than guarantee. Venus is technically in the Sun's habitable zone, yet its surface is hot enough to melt lead, with atmospheric pressure 90 times that of Earth and clouds of sulfuric acid. Mars is near the outer edge, and while it was once warmer and wetter, it's now cold and dry with a thin atmosphere. So location is necessary but not sufficient. A planet also needs the right mass to hold an atmosphere, the right atmospheric composition to trap heat without trapping too much, protection from deadly radiation, geological activity to recycle chemicals and maintain a stable climate over eons, and probably a magnetic field to shield it from stellar wind that can strip away atmospheres. The concept of the habitable zone has evolved. Early definitions focused purely on temperature, calculating where liquid water could exist based on stellar heating. But we now understand that planetary characteristics matter just as much. A planet's albedo, how much sunlight it reflects, affects how much heat it retains. Greenhouse gases like carbon dioxide and methane trap heat, warming the planet. Clouds can reflect sunlight, cooling the planet, or trap heat, warming it, depending on their altitude and composition. Tidal heating from a nearby star or other planets can provide additional warmth. And subsurface oceans, like those possibly existing on Europa or Enceladus in our solar system, show that life might not even need surface water. Some researchers have proposed a photosynthetic habitable zone, recognizing that on Earth, oxygenic photosynthesis, the process by which plants and cyanobacteria produce oxygen, requires not just water, but also sufficient light in the right wavelengths, between 400 and 700 nanometers. Around very cool red dwarfs, the habitable zone might be too dim for Earth-like photosynthesis, limiting the production of oxygen and thus the development of complex ecosystems. This doesn't rule out life, but it might constrain what kind of life could evolve. Red dwarf stars, the most common type in the galaxy, present both opportunities and challenges. Because they're small and dim, their habitable zones are very close, and planets there orbit rapidly, making them easier to detect with both transit and radial velocity methods. Many nearby red dwarfs have confirmed planets in their habitable zones, including Proxima Centauri b, the closest known exoplanet to Earth at just 4.2 light-years away. However, planets in these tight orbits are likely tidally locked, meaning one hemisphere always faces the star while the other is in perpetual darkness. This could create extreme temperature gradients unless the planet has a thick atmosphere to redistribute heat. Additionally, red dwarfs, especially young ones, are prone to powerful flares that release intense bursts of X-rays and ultraviolet radiation. These flares could damage or strip away atmospheres, making habitability challenging. K-type stars, slightly cooler and smaller than our Sun, might offer a sweet spot. They're more stable than red dwarfs, with longer lifespans than Sun-like G-type stars, giving more time for life to evolve. Their habitable zones are at moderate distances, avoiding the tidal locking and radiation issues of red dwarf planets. And they're abundant, making up about 13% of stars in the galaxy. Some astronomers believe K-type stars may be the best places to search for life. Finding habitable zone planets is a major goal of exoplanet science, but it's only the first step. We need to characterize their atmospheres, determine their compositions, measure their masses and densities, and look for signs of geological activity. We need to know if they have water, not just in principle but in reality. And ultimately, we want to know if any harbor life. That's a far more challenging question, one that will require not just finding these planets, but studying them in extraordinary detail, looking for biosignatures, atmospheric gases that could indicate biological processes. TRAPPIST-1. 7 worlds, 1 star. No planetary system has captured the imagination and scientific attention quite like TRAPPIST-1. Discovered in 2017, this system contains 7 Earth-sized planets orbiting a tiny red dwarf star just 40 light-years from Earth in the constellation Aquarius. It's the most compact multi-planet system known, and 3 of the planets orbit in the habitable zone. The discovery was announced at a NASA press conference and splashed across news headlines worldwide. Here, in this one small system, was a miniature solar system of rocky worlds, several potentially capable of hosting liquid water and perhaps life. TRAPPIST-1, the star, is what's called an ultra-cool dwarf, a star barely massive enough to sustain nuclear fusion. It's about the size of Jupiter, just 11% the mass of the Sun, and its surface temperature is only about 2,500 degrees Celsius compared to the Sun's 5,500 degrees. It's so cool and dim that its habitable zone lies very close in. All 7 planets orbit closer to their star than Mercury orbits the Sun, the innermost at just 1.7 million kilometers, the outermost at 9.3 million. Yet because the star is so faint, the outermost planets receive less light than Mars gets from the Sun. The entire system could fit comfortably inside the orbit of Mercury, a testament to how different planetary systems can be. The planets are designated TRAPPIST-1b through H, with B being closest to the star. All 7 are roughly Earth-sized, with radii ranging from 0.77 to 1.113 times Earth's radius. Their masses range from about 0.3 to 1.3 Earth masses. From their sizes and masses, astronomers have calculated their densities, which suggest all 7 are rocky worlds, likely composed primarily of iron, rock, and possibly water. Some may have significant amounts of water, perhaps much more than Earth, existing as atmospheric water vapor for the inner planets, liquid oceans for the mid-range planets, and ice for the outer planets. TRAPPIST-1e, the 4th planet from the star, is particularly intriguing. It's almost exactly Earth's size, with 92% Earth's radius and 77% Earth's mass. It receives about 60% of the sunlight Earth receives, slightly less, but well within the habitable zone. Its estimated surface temperature ranges from 225 to 246 Kelvin, or -48 to -27 degrees Celsius, depending on its atmospheric properties. With a substantial greenhouse effect, perhaps from carbon dioxide or methane, the planet could be much warmer, potentially allowing liquid water on its surface. TRAPPIST-1f and G, the 5th and 6th planets, also reside in the habitable zone. The 7th planet, H, is likely too cold, its surface frozen. Because the TRAPPIST-1 planets are so close to each other and to their star, they exert gravitational influences on one another. These interactions cause slight variations in their orbital periods and transit times, a phenomenon called transit timing variations. By carefully measuring these variations, astronomers have refined the masses of the planets with impressive precision. The TRAPPIST-1 system is gravitationally harmonious, with the planets locked in a resonance, their orbital periods related by simple ratios. For every 8 times planet B orbits the star, planets C, D, E, F, G, and H complete 5, 3, 2, 1, 1.5. 1 and 3/4 orbits respectively. This resonance stabilizes the system, preventing close encounters that could disrupt orbits. The planets are almost certainly tidally locked, meaning each shows the same face to the star at all times, just as the Moon shows the same face to Earth. This would create a permanent day side and night side. The day side would be illuminated by a dim red sun hanging motionless in the sky, heating the surface beneath it. The night side would be in eternal darkness, potentially much colder. However, atmospheric models suggest that if the planets have substantial atmospheres, winds could transport heat from day to night, moderating the temperature differences and potentially allowing habitable conditions in the twilight zones between eternal day and eternal night. Standing on one of these planets, based on our understanding of optics and atmospheric physics, the sky would be a deep, dusky red during the day, the star appearing about 4 times larger than the Sun appears from Earth. And the other planets would be visible, sometimes appearing larger than the Moon in Earth's sky. Eclipses would be common, as planets frequently pass in front of one another. The system is so compact that the planets would appear not as mere points of light, but as discernible disks, their phases changing as they orbit. You could watch neighboring worlds cross the face of the Sun or see them lit by reflected starlight at night. It would be a sky unlike any we know, a dance of worlds in perpetual motion. The TRAPPIST-1 system has been observed extensively by ground-based telescopes, the Hubble Space Telescope, the Spitzer Space Telescope, and now the James Webb Space Telescope. These observations have searched for atmospheres, a crucial step in determining habitability. Early observations suggested the inner planets, B and C, have likely lost any atmospheres they once had, stripped away by stellar radiation, and perhaps never replenished. TRAPPIST-1b has been measured to have an extremely high dayside temperature and no substantial atmosphere. TRAPPIST-1c similarly shows no evidence of a thick atmosphere. But for the planets in the XOA habitable zone, the question remains open. James Webb observations of TRAPPIST-1d just inside the habitable zone have been inconclusive, neither confirming nor ruling out an atmosphere. The planet is close to the threshold where atmospheres might survive or be stripped away. For TRAPPIST-1e, the most Earth-like of the 7, observations are planned or underway. If this planet has a substantial atmosphere, it would be a major step forward. TRAPPIST-1f and G are also high-priority targets. These observations are challenging because the planets are small, their stars are faint, and the atmospheric signals are subtle. But with sufficient telescope time and advanced analysis, we're on the cusp of knowing whether these worlds are barren rocks or something more, places with weather, with chemistry, perhaps even with the conditions for life. Atmospheric secrets. Studying exoplanet atmospheres is one of the most exciting frontiers in astronomy. An atmosphere transforms a planet from a simple ball of rock or gas into a dynamic, complex world with weather, chemistry, and perhaps biology. By analyzing the light that passes through or reflects from an exoplanet's atmosphere, astronomers can determine what gases are present, how the atmosphere is structured, and what conditions prevail. The primary technique, transit spectroscopy, observes the slight dimming of starlight as a planet crosses in front of its star. Some of this starlight passes through the planet's atmosphere on its way to Earth. Different molecules in the atmosphere absorb light at specific wavelengths, leaving dark lines or bands in the spectrum. By comparing the spectrum during the transit with the spectrum when the planet is not transiting, astronomers can isolate the atmospheric absorption and identify which molecules are present. Water vapor, carbon dioxide, methane, ammonia, and other gases have distinctive spectral signatures. Emission spectroscopy works similarly, but observes the light emitted by the planet itself, primarily in the infrared. Just before and after the planet passes behind the star, a secondary eclipse, the total light from the system includes light from both the star and the planet. When the planet is eclipsed, hidden behind the star, only the star's light remains. The difference tells us how much light the planet itself emits or reflects. This allows astronomers to measure the planet's temperature and atmospheric composition on its day side. The James Webb Space Telescope has revolutionized atmospheric studies. Its infrared sensitivity and large mirror allow it to detect faint signals from exoplanet atmospheres with unprecedented precision. Webb can see molecules that were previously invisible to Hubble and Spitzer, particularly at longer infrared wavelengths where many important gases absorb. One of Webb's first exoplanet targets was WASP-39b, a Saturn-sized gas giant about 700 light-years away, orbiting very close to its star. Webb's observations revealed a rich soup of atmospheric constituents: water vapor, carbon dioxide, carbon monoxide, sodium, potassium, and for the first time, sulfur dioxide. The detection of sulfur dioxide was groundbreaking because it can only be formed through photochemistry, chemical reactions driven by high-energy ultraviolet light from the star. On Earth, photochemistry in the atmosphere produces ozone from oxygen. On WASP-39b, photochemistry transforms sulfur-bearing compounds into sulfur dioxide. This discovery proved that exoplanet atmospheres are not just static mixtures of gases, but dynamic, active systems where chemistry continuously reshapes the composition. It showed that Webb could detect not just simple molecules, but the products of complex atmospheric processes. Webb has also observed WASP-18b, an ultra-hot Jupiter, where temperatures exceed 2,800 degrees Celsius. These observations revealed temperature variations across the planet's atmosphere, including differences between the eternal morning and eternal evening on this tidally locked world. The evening side is about 200 degrees Celsius hotter than the morning side, likely due to the circulation patterns that carry heat from the intensely heated day side around the planet. Three-dimensional mapping of temperature and composition is becoming possible, turning these distant worlds into real places with structure and dynamics. Another remarkable target is K2-18b, the super-Earth or mini-Neptune orbiting in the habitable zone of its red dwarf star. Webb detected carbon dioxide and methane in its atmosphere, a combination consistent with a hydrogen-rich atmosphere over a water-rich interior, the Hycean planet scenario. More provocatively, Webb tentatively detected dimethyl sulfide, DMS, a molecule that on Earth is produced almost exclusively by marine phytoplankton. DMS in K2-18b's atmosphere, if confirmed, could be a biosignature, evidence of biological activity. However, caution is essential. The detection is tentative, requiring further observations to confirm. And even if confirmed, alternative explanations must be ruled out. Exotic chemistry, perhaps driven by the planet's unusual conditions, might produce DMS without life. But if it is a biosignature, K2-18b could be the first planet beyond Earth known to harbor life, even if it's microbial life in an alien ocean beneath a thick hydrogen sky. For rocky planets, detecting atmospheres is harder. Rocky worlds, especially small ones, have thinner atmospheres that produce weaker signals. 55. Cancri E, the super-Earth with a surface possibly molten, shows signs of a substantial atmosphere, likely carbon dioxide or carbon monoxide bubbling up from its magma ocean. This was unexpected. Many thought such a hot planet would lose its atmosphere quickly, but if the atmosphere is constantly replenished from below, it can persist. This discovery has implications for understanding how rocky planets retain or lose their atmospheres under extreme conditions. TRAPPIST-1. Planets, despite extensive observations, have not yet revealed clear atmospheric signatures for most of them. The planets are small, the star is faint, and the signals are at the limits of what current instruments can detect. But with more telescope time and refined techniques, atmospheres may yet be detected. If they are, the next step is to characterize them, to measure not just the presence of gases but their abundances, to look for signs of liquid water, greenhouse warming, or even biosignatures like oxygen and methane existing simultaneously in disequilibrium. Biosignatures are gases or combinations of gases that could indicate life. On Earth, oxygen is abundant in the atmosphere because photosynthetic organisms produce it continuously. Without life, oxygen reacts with rocks and gases, disappearing over time. Similarly, methane is constantly produced by microbes and removed by chemical reactions. The simultaneous presence of oxygen and methane, or other gas combinations that wouldn't coexist without constant replenishment, could be powerful biosignatures. Phosphine, a gas detected tentatively in Venus's atmosphere and subject to ongoing debate, is another potential biosignature because it's difficult to produce abiotically in significant quantities. Finding such gases on an exoplanet, especially one in the habitable zone, would be strong, though not conclusive, evidence for life. Formation and evolution. Understanding how planets form and evolve helps us interpret the incredible diversity of exoplanets. Planets are born in protoplanetary disks, vast clouds of gas and dust that swirl around newborn stars. As the disk cools, dust grains stick together through electrostatic forces and gentle collisions, growing from microscopic particles to pebbles to boulders to kilometer-sized planetesimals. These planetesimals collide and merge, building up protoplanets, which continue to grow by sweeping up surrounding material. In the inner regions of the disk, close to the star, temperatures are high, and only materials with high melting points, like metals and rocky silicates, can condense. This is where terrestrial planets form, worlds of rock and metal like Earth and Mars. Beyond the snowline, the distance from the star where water and other volatiles freeze into ice, the available material increases dramatically. Ice grains provide more building blocks, and planets can grow larger and faster. The cores of giant planets like Jupiter likely formed just beyond the snowline, becoming massive enough to attract huge atmospheres of hydrogen and helium from the surrounding nebula. But formation is only the beginning. Planets can migrate, changing their orbits due to gravitational interactions with the disk or with other planets. Type 1 migration affects planets still embedded in the disk. As a planet orbits, it clears a partial gap in the disk, creating a spiral density wave. The gravitational interaction with this wave causes the planet to slowly spiral inward toward the star. Type 2 migration affects more massive planets that open full gaps in the disk. These planets are dragged inward as the disk itself accretes onto the star. Migration explains hot Jupiters. These giant planets formed far from their stars, where ice and gas were abundant, but then migrated inward, their orbits shrinking over millions of years. Some may have migrated smoothly through the disk. Others may have been flung inward by gravitational encounters with other planets in chaotic early planetary systems. Once close to the star, tidal forces circularize the orbit, locking the planet into a stable configuration. But migration can also strand planets or eject them entirely. Some planets migrate too close and fall into their stars. Others are flung outward into distant orbits or even ejected from the system, becoming rogue planets. Planetary systems can be dynamically unstable. Multiple planets interacting gravitationally can destabilize one another, leading to close encounters, collisions, or ejections. Computer simulations suggest that many planetary systems go through violent reorganizations before settling into stable configurations. Our solar system likely experienced such events. The NICE model, named for the French city where it was developed, proposes that the orbits of Jupiter, Saturn, Uranus, and Neptune were once very different, and a gravitational instability about 600 million years after the solar system formed caused them to migrate, Jupiter inward slightly, the others outward significantly. This migration scattered smaller bodies, causing the late heavy bombardment, a period of intense impacts on the inner planets recorded in the lunar cratering record. The final architecture of a planetary system depends on many factors: the mass and composition of the protoplanetary disk, the formation and migration history of the planets, interactions between planets, and interactions with the disk itself. This explains why exoplanet systems are so diverse. Each system has its own history, its own sequence of events that led to the configuration we observe today. Planetary evolution continues long after formation. Atmospheres change. Volcanic activity releases gases, building up atmospheres on rocky planets. Impacts deliver water and organic molecules. Stars evolve, growing brighter over time, changing the radiation environment. For planets with life, biological processes can dramatically alter atmospheres, as Earth's oxygen-rich atmosphere demonstrates. Tectonic activity recycles elements, maintains atmospheric balance, and may be essential for habitability over geological timescales. The role of a planet's magnetic field cannot be overstated. Earth's magnetic field, generated by convection in its liquid iron outer core, shields our atmosphere from the solar wind, a stream of charged particles flowing from the sun. Without this protection, the solar wind would gradually strip away atmospheric gases, eroding the atmosphere over millions of years. Mars likely lost much of its atmosphere this way after its core cooled and its magnetic field shut down billions of years ago. For exoplanets, especially those orbiting close to active stars with strong stellar winds, magnetic fields may be crucial for atmospheric retention and long-term habitability. Whether exoplanets have magnetic fields depends on their internal structure, composition, rotation rate, and thermal evolution. Factors we're only beginning to understand through theoretical models and observations. The delivery of volatiles, substances like water, carbon dioxide, and organic molecules that vaporize at relatively low temperatures, is another crucial aspect of planetary evolution. In the inner regions of protoplanetary disks, it's too hot for water to condense, so terrestrial planets form dry. Water and other volatiles must be delivered later, either by comets and asteroids that formed in the colder outer disk and were then scattered inward, or by migration of ice-rich planetesimals. The late heavy bombardment in our solar system, a period of intense impacts about 3.8 to 4.1 billion years ago, may have delivered significant water and organic material to Earth. Similar bombardment epochs likely occur in other planetary systems, potentially seeding rocky planets with the ingredients for life. Some planets lose their atmospheres entirely. Small planets with weak gravity struggle to hold on to light gases like hydrogen and helium. intense stellar radiation, especially from young stars, can heat atmospheres and drive atmospheric escape. On Venus, a runaway greenhouse effect evaporated the oceans, filling the atmosphere with water vapor, which was then broken apart by sunlight, and the hydrogen escaped to space, leaving behind a dense carbon dioxide atmosphere. On Mars, the thin atmosphere may have been stripped away by solar wind after the planet's magnetic field shut down. James Webb Space Telescope discoveries. The James Webb Space Telescope, launched in December 2021, represents the most powerful observatory ever sent to space for studying exoplanets. With its large 6.5-meter primary mirror and suite of sensitive infrared instruments, Webb can detect the faint light of exoplanets and analyze their atmospheres with unprecedented detail. The telescope orbits the Sun at the second Lagrange point, L2, about 1.5 million kilometers from Earth, where it's shielded from the Sun's heat and light by a massive sun shield, keeping its instruments cold enough to detect faint infrared signals. Since beginning science operations in 2022, Webb has observed dozens of exoplanets, revealing new details about their atmospheres, temperatures, and compositions. One of Webb's early triumphs was measuring the temperature of TRAPPIST-1b, the innermost planet of the TRAPPIST-1 system. Webb found a dayside temperature of about 508 Kelvin, or 235 degrees Celsius, far too hot for liquid water and consistent with a bare rock, with little to no atmosphere. This measurement ruled out certain atmospheric scenarios and showed that Webb could precisely measure planetary temperatures even for small, rocky worlds. Webb observed HD 199733b, a hot Jupiter known for extreme weather, and detected hydrogen sulfide in its atmosphere, the molecule responsible for the smell of rotten eggs. On Earth, hydrogen sulfide is produced by volcanic activity and biological processes. On HD 199733b, it's likely a primordial component of the planet's composition, retained from the nebula in which the planet formed. The detection of hydrogen sulfide, along with water, carbon dioxide, and carbon monoxide, allows astronomers to reconstruct the planet's chemical inventory and compare it to predictions from formation models. WASP-39b, mentioned earlier, was one of Webb's showcase targets for demonstrating the telescope's atmospheric capabilities. The comprehensive analysis revealed not only the atmospheric constituents, but also evidence of cloud formation, photochemistry, and temperature structure. Webb detected sulfur dioxide, a molecule created when sulfur-bearing gases are broken apart by ultraviolet light and recombine. This photochemical process is similar to how ozone forms in Earth's stratosphere, showing that chemical reactions driven by starlight actively shape exoplanet atmospheres. Webb has also mapped temperature variations on WASP-18b, an ultra-hot Jupiter, revealing a planet with a permanent day side and night side due to tidal locking. The evening side of the planet, where air has been heated and carried around from the intensely irradiated day side, is hotter than the morning side, where cooler air is being drawn in. These observations allow astronomers to study atmospheric circulation and heat transport on an alien world 400 light-years away, turning a distant planet into a laboratory for atmospheric physics. The detection of carbon dioxide and methane in K2-18b's atmosphere hints at a water-rich world beneath a hydrogen atmosphere. K2-18b orbits in the habitable zone of its star, and the presence of water-related chemistry makes it a priority target for follow-up observations. The tentative detection of dimethyl sulfide, if confirmed, would be the first detection of a potential biosignature on an exoplanet, though much work remains to verify the result and rule out alternative explanations. For 55 Cancri E, Webb detected an atmosphere likely composed of carbon dioxide or carbon monoxide, suggesting a volatile, rich environment despite the planet's extreme heat. This was unexpected. Theory suggested that such a hot, close planet should lose its atmosphere quickly. But if the atmosphere is continuously replenished from a subsurface magma ocean, it can persist, bubbling up from below as fast as it escapes to space. This discovery challenges models of atmospheric retention and shows that planets can maintain atmospheres through processes we're still learning to understand. Webb's capabilities will improve as astronomers gain experience with the instruments and develop new observational strategies. Longer observation times will improve signal-to-noise, allowing detection of fainter features. Multiple observations of the same planet at different phases or seasons will reveal variability, weather, and long-term changes. Coordinated observations with ground-based telescopes will provide complementary data. And as Webb observes more planets, patterns will emerge, allowing statistical comparisons between different types of planets, different host stars, and different orbital configurations. Webb is also observing planetary systems in formation, imaging protoplanetary disks around young stars, and detecting gaps and spirals carved by nascent planets. One system, PDS-70, has been directly imaged with 2 giant planets still embedded in the disk, accreting material and carving gaps. These observations provide snapshots of planet formation in action, showing how planets emerge from disks and modify their environments. The search for life. The ultimate goal of exoplanet research is to determine if life exists beyond Earth. This is one of humanity's oldest and most profound questions. For millennia, we could only wonder. Now, for the first time, we have the tools to search, to gather evidence, and perhaps to find an answer. Life as we know it requires several ingredients: liquid water, a source of energy, organic molecules, and sufficient time for chemistry to become biology. Many exoplanets likely have these ingredients. Water is common in the universe, found in comets, asteroids, and in the atmospheres of gas giants. Organic molecules, carbon-based compounds, form readily in space and have been detected in protoplanetary disks and comets. Energy comes from stars, from geothermal heat, or from chemical reactions. And time is abundant. The universe is 13.8 billion years old, and planets have existed for most of that time. The Drake equation, formulated in 1961 by astronomer Frank Drake, attempts to estimate the number of communicative civilizations in the galaxy. It multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction on which life arises, the fraction where intelligent life evolves, the fraction that develops technology detectable across interstellar distances, and the length of time such civilizations transmit signals. Each factor is uncertain, but the discovery of exoplanets has constrained some terms. We now know that most stars have planets, and that habitable zone planets are common. The bottleneck is likely the probability that life arises, and even more so, that it evolves intelligence and technology. Biosignatures are the key to detecting life on exoplanets. These are observational indicators that could result from biological processes. The most robust biosignatures are atmospheric gases that wouldn't persist without life. Oxygen is the classic example. Earth's atmosphere is 21% oxygen, produced almost entirely by photosynthesis. Without life, oxygen would react with surface rocks and volcanic gases, disappearing within a few million years. An oxygen-rich atmosphere on a rocky planet in the habitable zone would be strong evidence for life, though not conclusive. Geochemical processes can produce limited oxygen, and we must rule out false positives. Methane combined with oxygen is an even stronger biosignature. These gases react with each other, so their coexistence implies continuous production. On Earth, methane comes largely from microbes and geological processes, while oxygen comes from photosynthesis. Finding both together on an exoplanet, especially in the presence of water vapor, would be highly suggestive of life. Other potential biosignatures include phosphine, dimethyl sulfide, and even molecular oxygen combined with methane and water in specific ratios. But biosignatures must be interpreted carefully. Photochemistry, volcanism, and unusual atmospheric conditions can produce misleading signals. Confirmation requires multiple lines of evidence, multiple biosignature gases, observations at different wavelengths, understanding the planet's overall environment, and ruling out abiotic explanations. Technosignatures are signs of technology, potentially even more compelling than biosignatures. If an advanced civilization builds radio transmitters, generates significant heat, modifies its planet's atmosphere through industrial processes, or constructs megastructures like Dyson spheres, we might detect these signs. SETI, the search for extraterrestrial intelligence, scans for radio or optical signals that could indicate technology. So far, no confirmed technosignatures have been found, but the search continues and is expanding to new frequencies and methods. Proxima Centauri b, the nearest exoplanet, is an obvious target. At just 4.2 light-years away, it's close enough that powerful telescopes could study it in detail. But Proxima Centauri is a red dwarf, and the planet is tidally locked. Whether it has an atmosphere and whether conditions are suitable for life remain open questions. Future missions may directly image Proxima Centauri b, taking pictures that show its color, look for seasonal changes, and detect atmospheric composition. Several space missions are planned or proposed to advance the search for life. The Nancy Grace Roman Space Telescope, launching in the late 2020s, will have a coronagraph to demonstrate direct imaging of exoplanets. The Habitable Worlds Observatory, a future mission still in the planning stages, would be optimized for finding and characterizing Earth-like planets in the habitable zones of nearby stars, searching for biosignatures in their atmospheres. Ground-based telescopes are also advancing. The extremely large telescope, being built in Chile with a 39-meter primary mirror, will be able to detect oxygen in exoplanet atmospheres through transit spectroscopy. The discovery of life would profoundly change our understanding of biology, philosophy, and our place in the universe. If life arose independently on another planet, it would suggest that life is common, that the origin of life is not an improbable accident, but a natural outcome of planetary evolution. If that life is complex, multicellular, or intelligent, it would suggest that evolution can produce similar outcomes on different worlds. And if we detect a technological civilization, it would open the possibility of communication, of learning from another intelligence, of joining a galactic community. Our place in the cosmos. The discovery of exoplanets has transformed how we see ourselves. For most of history, Earth was the center of the universe, the only world that mattered. Even after Copernicus and Galileo showed that Earth orbits the Sun, and even after we realized the Sun is just one star among billions in the galaxy, we had no proof of other planets. Our solar system, with its 8 worlds, was unique as far as we knew. Now, we know we live in a universe teeming with planets. They are everywhere, around nearly every star, in every direction we look. Billions in our galaxy alone, and countless more beyond. Earth is one world among an uncountable multitude. This is humbling. We are not special in location, not placed at the center by design. We orbit an ordinary star in an ordinary part of an ordinary galaxy. We are, in Carl Sagan's words, a pale blue dot, a mote of dust suspended in a sunbeam. And yet we are also special. Of all the planets we've found, none is quite like Earth. None has the same combination of size, temperature, atmosphere, and liquid water oceans teeming with life. We've found hot Jupiters and ice giants, lava worlds and frozen snowballs, planets with thick hydrogen atmospheres and planets with no atmospheres at all. But we haven't yet found another Earth, a blue-green world with continents and oceans, forests and deserts, a biosphere rich with complex life. Such a planet may exist, likely does exist, but we haven't found it yet. Earth's uniqueness may be temporary, an artifact of our limited technology. As telescopes improve and surveys continue, we will find more planets like ours. Earth-sized rocky worlds in habitable zones are common, perhaps numbering in the billions in the galaxy. The Kepler mission estimated that about 20 to 50% of Sun-like stars have a roughly Earth-sized planet in the habitable zone. If even a fraction of these are truly Earth-like, with water, atmospheres, and stable climates, there could be millions of worlds where life might arise. The discovery of exoplanets raises profound questions. Why does life exist here? Is it common or rare? Are we alone? Or is the galaxy filled with life, perhaps even intelligent life? If life is common, why haven't we detected it? The Fermi paradox asks, if intelligent civilizations are common, where are they? Why haven't we seen evidence of their existence? Possible answers range from the cheerful, "We're among the first. Life has only recently become possible in the universe," to the sobering, "Civilizations self-destruct before reaching the stars," to the lonely, intelligent life is extraordinarily rare, and we may be alone in the observable universe. But we're still searching. Every new exoplanet, every atmospheric analysis, every refinement of our models brings us closer to understanding our place. We're learning that the universe is more diverse, more surprising, and more full of possibility than we imagined. We're learning that planets are not rare treasures, but common features of star systems. We're learning that the conditions for life, at least the ingredients, are widespread. And we're developing the tools to detect biosignatures, to find out if life exists elsewhere, to answer the question that has driven human curiosity since we first looked up at the stars and wondered. The exoplanets we've discovered are more than scientific data. They are real places, worlds as real as the one beneath our feet. Some are hells of fire and pressure. Others are frozen in eternal darkness. But some, perhaps, are gardens, worlds where rivers flow, where rain falls, where something stirs in the waters or drifts on the winds. We may never visit them. The distances are too vast. Even Proxima Centauri b, our nearest neighbor, is over 4 light-years away, more than 40 trillion kilometers. With current technology, a spacecraft would take tens of thousands of years to reach it. But we can observe them. We can study their light, decode their atmospheres, and learn their stories. And in doing so, we learn about ourselves, about the planet we call home, about the forces that shaped us and the fate that awaits us. Exoplanets remind us that Earth is precious. It's the only world we know with life. The only place in the universe where we're certain life exists. It's our home, a fragile oasis in the vastness of space. Seeing the diversity of exoplanets, the range of conditions, the extremes of heat and cold, the violence and the silence, makes us appreciate how remarkable our own planet is. How lucky we are to have a stable star, a protective magnetic field, an atmosphere that warms but doesn't overheat, oceans that cover the surface but don't drown the land, a moon that stabilizes our tilt, and a biosphere that has persisted for billions of years. The search for exoplanets is ongoing. New missions are planned. New techniques are being developed. The next generation of telescopes will be even more powerful, capable of finding smaller planets, studying fainter stars, and detecting subtler signals. We're entering an era where we may finally answer the question, Are we alone? And whatever the answer, it will change us. If we find life, even microbial life, it will confirm that the universe is alive, that biology is not unique to Earth. If we don't, if we search and find silence, it will make Earth seem even more precious, a sanctuary in an otherwise barren cosmos. Drifting now gently through these thoughts, let yourself rest in the knowledge that the universe is vast and full of wonders. Out there, orbiting distant suns are worlds beyond imagining. Some may be like Earth, others may be unlike anything we've conceived. But each is a piece of the cosmic story, a chapter in the unfolding narrative of the universe. And here, on this small blue world, we have the privilege of looking out, of seeking, of wondering. The stars are no longer just points of light. They are suns with families of their own. And among them, perhaps, are worlds where someone else looks up and wonders the same things we do. Tonight, as you settle into sleep, know that you live in an age of discovery. An age when planets that once existed only in imagination are being found and catalogued, studied, and understood. An age when the question of life beyond Earth is not a matter of philosophy, but of observation. The exoplanets are out there, silent and patient, waiting to be explored. And though we may never walk on their surfaces, we are learning their secrets, one photon of light at a time. But here's the twist, the revelation that changes everything we've discussed tonight. We are exoplanets too. Think about it. To any astronomer on a world orbiting Proxima Centauri, our Earth is an exoplanet. To someone on a planet in the TRAPPIST-1 system, our Sun is just another star in their sky, and Earth is a distant world they might detect through the transit method, watching as we periodically cross the face of our star, blocking a tiny fraction of its light. They might analyze the starlight passing through our atmosphere and detect oxygen, nitrogen, water vapor, methane. They might puzzle over the oxygen-methane combination, this disequilibrium that seems to require constant replenishment. They might wonder, as we wonder now, whether those gases indicate life. Every discovery we've explored tonight, every method we've developed, every observation we've made, turns the mirror back on ourselves. We're not observers standing outside the system, we're participants. Earth is one exoplanet among billions, circling one star among hundreds of billions. The same physics that governs 51 Pegasi b governs us. The same chemistry that might create life on K2-18b created life here. The same gravitational forces that shape hot Jupiters and super-Earths shaped our world. When we search for exoplanets, we're not just exploring out there, we're exploring the nature of planetary systems themselves. And by extension, we're understanding Earth's story more deeply. Every atmospheric measurement of a distant world helps us understand our own atmosphere. Every discovered planet teaches us about the possible fates of Earth, about what might have been, and what still could be. The exoplanet with a runaway greenhouse effect shows us one possible future if we're not careful. The tidally locked world reminds us how lucky we are to have a gentle rotation and a stabilizing moon. The planets that lost their atmospheres reveal how precious and fragile our own air truly is. This is the ultimate revelation. In seeking to understand worlds beyond our solar system, we've gained a mirror, a way to see ourselves not as the center of everything, but as one example among countless variations. One experiment in planetary evolution. One possibility realized among an infinite array of other possibilities. Some worlds in this cosmic gallery are hells. Others are frozen wastes. But a few, scattered across the galaxy like precious gems, might be sanctuaries for life, for complexity, for consciousness. And if we do find life out there, even microbial life in the oceans of some distant Hycean world, it won't diminish us. It will illuminate the profound truth that life is not an accident unique to Earth, but a natural consequence of planetary evolution, as inevitable as the formation of stars from clouds of gas and dust. We would learn that the universe is not just vast and ancient, but alive, filled with countless expressions of chemistry becoming biology, matter becoming life, life becoming awareness. Or perhaps we search and find only silence. Perhaps, despite billions of planets, despite oceans and atmospheres and energy sources, life is exceedingly rare. Perhaps consciousness is rarer still. In that case, Earth becomes not just precious but sacred, the one place in all the observable universe where the cosmos has awakened to contemplate itself, where atoms have assembled into structures that can wonder at the stars, that can build telescopes to peer into the depths of space, that can ask questions and seek answers. Either way, whether we find companions or confirm our solitude, the search has already changed us. We know now that we're not alone in having planets, that worlds are common, that the ingredients for life are scattered throughout the galaxy. We know that the universe is more creative, more diverse, more full of possibility than we ever imagined. And we know that our little blue world, this pale dot orbiting an ordinary star in an unremarkable part of the galaxy, is both ordinary and extraordinary. Ordinary in its existence, extraordinary in what it has produced. So as you drift toward sleep, carrying with you the knowledge of distant worlds and alien skies, remember this. You are an exoplanet explorer. Yes, but you're also an exoplanet resident. You live on one of those billions of worlds, one of the lucky ones where conditions aligned just right, where water could flow and life could emerge and consciousness could evolve. You are made of the same elements that compose all those distant planets, forged in the same stellar furnaces, scattered by the same supernovae, assembled by the same gravitational forces. The light from those distant worlds is touching you right now, just as the light from our sun is touching them. We're all connected by starlight, by gravity, by the laws of physics that govern everything. In studying exoplanets, we're really studying ourselves, understanding our origins, contemplating our place, and perhaps, just perhaps, preparing for the day when we detect that unmistakable signal, that combination of gases or that radio transmission that tells us we are not alone, that somewhere among the exoplanets is another consciousness, looking out at the stars and wondering just as we do what it all means. If these quiet journeys through the cosmos help you find rest, or if they spark a curiosity that lingers even as you drift toward sleep, consider subscribing to Sleepable Science. It helps others discover this peaceful corner of wonder, and it allows us to continue exploring the universe together, one sleepy evening at a time. Thank you for joining me tonight. Rest well, dream softly, and know that you're not just on Earth, looking out at the exoplanets. You're on an exoplanet, looking out at other Earths. Good night.